Okay, yeah, let's start. There's not too many people, but all right. Feel free to turn on your cameras. Yeah, so the second homework is due right now. The third one, is soon going to be, or it's already online. Yeah, it's basically posted. Due next Friday as usual. Yeah. So, okay, yeah, 4 people is the historic low, and I'm one of the 4. Okay, anyways, I'll send out some angry email about that. Okay, now it's 5. All right, so last time I stopped at talking about derangements. D of n is the number of derangements, which are, yeah, each derangement is just a permutation of bracket n without fixed points. So yeah, and the kind of the application that we found from the inclusion-exclusion principle is that the limiting probability as n goes to infinity of that your random, uniformly random permutation is a derangement is 1 over e. And while I'm here today, so I want to start by discussing a bunch of other, well, one other related problem where this number somehow magically appears. So, oh, Fridays are hard. Yeah, okay, that is true. But yeah, thanks, even though it's hard, thanks to those who came. Yeah, it's at some point there's going to be 0 people, and then there's going to be a sad lecture. But for now it's good. Yeah, so let me mention some other problem, which is actually one of my favorites because it's applicable to real life. So I just found out today that in the US it's called the secretary problem, which yeah, in Russia it's something like the bride, the princess problem, or the picky bride, whatever problem. But yeah, the setup is pretty simple. You are interviewing candidates. You want to hire a secretary, and then so you have n candidates for a job, and you are interviewing them one by one. So interview each one by one. And so once you interview a person, you immediately have to either make them an offer, or you only get to pick one person, and you have to do it right after the interview. Otherwise, they go elsewhere. So hire or reject each person right after each interview. And also, while you conduct your interviews in such a way that you can you kind of get full information about how this candidate compares to all the previous ones. And so you have seen 3 people, then the 4th one is going to be you can compare any 2 candidates once you interview them. So yeah, that's the setup, and then the goal, which is somewhat unusual but sort of ambitious, is you want to hire the absolute best possible candidate. So out of one, after you interview like all of them, you're gonna know which one was the best one, and there was only one of them which is the best. And then the goal is to kind of to choose the strategy of whether you hire or reject each individual person, so that you end up hiring the best one. And yeah, so and it's supposed to be somewhat large, like maybe 1 million or something. So that this seems very hard, right? You have to pick one out of 1 million, which are yeah. Anyways, and actually, I mean, in real life, you don't really apply this to like dating or hiring that much, but maybe like if you buy a car, for example, you're buying a used car, so you go all around the city and then you look at different cars, and then basically this situation kind of applies. You have to. It's not a good idea to just buy the first one. You have to kind of look around, and then after a certain point, you have to just pull the trigger and buy a car. So how do you optimize this? And yeah, so the question is, what is the optimal strategy? And what is the optimal success probability? What do you think is going to happen? I don't know the proof, but the answer is 1 over e. All right, yeah, there is a spoiler. The answer is 1 over e. That is indeed correct, which is crazy, right? There is a strategy which helps you find the absolute best candidate with probability 1 over e, which is quite large, right? It does not go to 0. Yeah, so the answer is going to be approximately 1 over e, which is approximately 37%. So yeah, you get to. The strategy is very good at choosing the best possible candidate. And so that's, and I'm not going to prove it either. So that you can look up the proof. It's in one direction it's not too hard, and the other it's a little bit harder. But yeah, anyways, so first here's the optimal strategy. The optimal strategy is that you have to you just hope the best candidate is in the last 1 over e. Oh, that's actually a good idea. That's almost it's almost the correct idea, except that you have to hope it's not in the first 1 over e candidates. So there is the number 1 over e appears twice in the theorem, and it's kind of surprising to me. So the strategy, yes, first of all you decide in advance that you're going to reject the first n over e candidates. Reject the first n over e candidates, which may not be an integer, so you candidates. And then you just after that you just look for the first person that's better than everybody before them. So after that, hire the first person which is better than everybody before them. Yeah, and the surprising fact is that the probability of success is 1 over, well, it's approximately 1 over e. It's always at least 1 over e, and as n gets large, it tends to 1 over e. So that's the theorem. And yeah, so I just want to mention this because it's a good strategy in life in general. You want to you can look at 10 cars, you skip the first maybe 3 of them, and then you just take the next one that's better than the first 3 of them. Yeah. Anyways, any questions on the princess problem? Does this have anything to do with the fact that limit of 1 to infinity? Yeah, does it have to do with derangement? And the answer is, I don't think so. Yeah, I think it's well, I mean, it all kind of, both of these have the same root, which is that, which is just that the exponential has a very nice series with the factorials. But yeah, I don't see how to connect this to derangements. But the answer is this, and again, there is, you can see that there 1 over e appears first here and then here, and it's not clear why these two numbers have to be related to each other, but they turn out to be related. So anyways, any other questions? Okay. No questions. All right, then I'm gonna just change the subject for a while. And now I'm gonna talk about partitions. And so previously I talked about set partitions, partitions of a set, but now I'm gonna talk about partitions of a number, which is actually it's something we've seen already in the first lecture a little bit. So a partition of n is a non-increasing, I'm gonna say weakly decreasing sequence lambda 1 greater or equal to lambda 2, etc., all the way up to lambda k of positive integers. Well, it has to, right, to define such that the sum lambda 1 plus lambda 2 plus etc. plus lambda k is equal to n. Right, so you want to represent n as a sum of positive integers. And yeah, and by the way, this, so I'm going to introduce some notation for partitions, and the sum of all parts, right? So these lambda i's are called parts of my partition, and then the sum is going to be denoted by the absolute value of lambda. Yeah, and another notation that's going to be convenient for us is we're gonna write that lambda, this symbol here, lambda is a partition of n. I'm going to denote it by this symbol here. So so you can ask, well, what is the I'm going to denote by p of n the number of partitions of n. Number of lambda, yeah. So it's just the same as the number of partitions of n. And so here is, hopefully I have a table. Okay. Yeah, so here's the table for the first several values. And maybe I should try, so p of 4 is equal to 5, because here are all the possible partitions of 4. So you can either have 4, or you can have 3 plus 1, or you can have 2 plus 2 plus, well, 2 plus 2, or 2 plus 1 plus 1, or you can have, what is it, 1 plus 1 plus 1 plus 1. Is that, yeah, that seems like I have 5 different, so that's just, I always sort these numbers, right? So the order kind of doesn't matter, and I sort them in weakly decreasing order. Okay, so, and another piece of notation is the length of lambda is the number of non-zero parts. Non-zero parts in my partition. So here this is one part, here I have two parts, and etc. Yeah, so a lot of notation. And finally, write p of n comma k. Similarly to the Stirling numbers, this is going to denote the number of partitions of n of length of partitions of n into k parts. Which I may or may not have a table here as well. Yeah, I think that's the table. So for example, if I'm looking at partitions of 4 into different number of parts, then I get 1, 2, 1. Right? So there's one partition into one part, two partitions into two parts, and then one partition into 3 and into 4 parts. Yeah. So okay, these look like the simplest possible objects we could study, but they are quite hard to count in general. Don't you mean length is equal to k? Oh, sorry. Yeah, okay. The length of lambda. Thank you. Length of lambda has to be equal to k. Yeah. So okay. So the point is that p of n is hard to count. To find an exact formula for these numbers is pretty hard, and even for these numbers here, it also, I mean, it's easier, but it's also hard. But one way to the easiest thing to do here is to find a recurrence relation. So let me start by explaining a very simple recurrence relation. So p of n comma k is equal to, you kind of want some sort of triangle rule to count. Yeah, let me just write down the recurrence, and then we'll try to guess what it's trying to tell us. P of n minus 1 comma k minus 1 plus p of n minus k comma k. So it's a little different, right, than the usual triangle, because you have to jump by k. So maybe, yeah, let's see if I can try. Maybe this 10 is equal to 5 plus 5. Right, so 11 is equal to 8 plus 3. And 10 is equal to 9 plus 1. So you always take the integer that's directly up and left of your integer, plus you jump by k. Whenever, yeah, so here this is column 5, so you jump by 5 up. That's the rule. So how do I prove this? If one appears or not. Oh, okay, yeah, that's correct. So you just look at the, yeah, thank you. So you look at just at the last part of lambda. If the last part is equal to 1, which, yeah, so if 1 appears among your partition, then remove it, and you get a partition of n minus 1 into k minus 1 parts. So you get p of n minus 1, k minus 1 ways to partition. And otherwise all parts are greater than or equal to 2, so you can decrease all parts by 1, and this way you get a partition of n minus k into the same number of parts. So yeah, that is I think the only easy. Yeah, there's going to be a few easy results today, but at some point I'm going to talk about something that's hard. So yeah, and by convention, I know I'm going to forget about this later, so let me mention this now. So usually, I'm going to usually refer to, I'm just going to set alpha I to be 0 for I bigger than the length of lambda. So even though originally I defined it as a sequence of positive integers, I can just kind of extend it by 0 all the way to infinity. And so yeah, partitions like 4, 2, 1, 1. This is the same thing as 4, 2, 1, 1, 0, 0, 0. Yeah, I consider these to be like equivalent as partitions. And so to each partition, I'm going to associate a Young diagram. Young diagram, which you just so if you have a partition 4, 2, 1, 1, then you put 4 boxes in the first row, 2 boxes in the second row, and so you put lambda I boxes in row I for each I, and the boxes are left aligned. Right, so you basically have like a corner, and then you put some boxes in the corner where you have gravity, which pulls all your boxes to the northwest. And so Young diagrams are very useful when you think about partitions and you want to figure out some bijections or whatever. It's usually a lot of times it's geometric, using some operations on the Young diagram like this. And one natural operation on the Young diagram, which is completely non-trivial on the actual numbers, is conjugation. Conjugation is the operation of, so if lambda is a partition, then the conjugate partition, which is denoted by lambda prime, is well, it's not easy to explain it using the numbers, but if I just talk about Young diagrams, has Young diagram obtained from the Young diagram of lambda by reflecting along, let me call it the main diagonal, as for matrices. So the main diagonal, it goes this way. This is the main diagonal. So maybe let me try some bigger example. Lambda 5, 2, 1, 1. Yeah, maybe, or even 5, 3, 1, 1. So I draw the Young diagram. Oops, it looks like this. Then I just reflected with respect to this line here. So I'm gonna get something like this. Yeah, 4, 2, 2, 1, 1. So lambda prime is 4, 2, 2, 1, 1. Is it clear, or should I? All right, cool, thanks. Yeah, and so you can use conjugation to prove some simple statements. So let me give you some examples of statements you can prove just by conjugating the partition. So the first part is that for each k and n, the number of partitions of n, such that the partitions into at least k parts is equal to the number of partitions of n whose the first part is at least k. Or, so that's one statement. Here's another statement, which is that for all n, the number of partitions such that the first part is equal to the second part is equal to the number of partitions for which all parts are at least 2. So you can see that if you conjugate any partition with at least k parts, then the number of parts becomes the first part of the number of parts becomes the first part of the new partition, of the conjugate partition, and etc. So you get all these easy statements, and you kind of it's a good idea to just internalize this conjugation operation to it's like an easy symmetry of all these problems for Young diagrams. And there is, of course, some partitions are self-conjugate, like, for example, this one here. And so one of your homework problems is going to be about self-conjugate partitions like this. Yeah, you can use Young diagrams to kind of find some nice bijections, as is going to be abundantly evident from the homework. All right, now I think this was all sort of trivial. Let me try to prove something extremely non-trivial. So I'm gonna let me try to talk about partitions into distinct parts. So let me denote P of P sub d even of n to be the number of partitions of n into an even number of distinct parts. And similarly, for odd, into an odd number of distinct parts. So the 2 points are that you fix the parity of the number of parts, and you also require that all parts are even, which is also going to be something like this is going to be in your homework. So I have a table, which I had to, actually this one I couldn't, wait, hold on, where is, okay. This one I couldn't really, couldn't Google the exact table like this, so I had to write a program which produces it. So anyways, here is, for each n and k, so here is n and here is k, I'm going to denote, I'm going to write down the, basically these are the number of partitions of n into k distinct parts. So for now, forget about the parity and just look at the, for each k, I can look at partitions into k distinct parts. So maybe, let's see, there should be this number here, there should be 3 partitions of 7 into 2 distinct parts. And indeed, 7 is 6 plus 1, right? Or 5 plus 2, or 4 plus 3. So that's the 3 possible ways. Is it clear what I'm doing? Okay, and yeah, and so the idea now is to look at the difference between these two numbers. So, which in other words, you take all numbers in the odd positions and you subtract them from the sum of the numbers in the even positions. So, for example, here -1 plus 3 minus 1 plus 3 minus 1 is equal to 1. And -1 plus 3 minus 2 is equal to 0, and etc. So you look at this pattern here, and it's kind of non-trivial, right? You get a bunch of -1s and a bunch of 1s, and the rest are zeros. So yeah, that's the next theorem. The next theorem is going to describe this pattern in the rightmost column, which if you look at it and you just try to guess what are the ends, for 1, 2, it's -1. For 5 and 7, it's +1. For 12 and 15, it's -1. And the next one is going to be like 22 or something like this. So yeah, here's that's called the Euler pentagonal theorem. Euler pentagonal theorem, which tells you that the difference between the even and the odd partitions into distinct parts is either +or -1 or 0. So it's -1 to the j if n is equal to j times 3j +or -1 over 2, and 0 otherwise. So that's kind of okay. So why is it called the pentagonal? Yeah, should I try an example? Maybe. Okay, so 3. What is j supposed to be? J and n. So if j is equal to 1, then 1 times 3, 1 times 3 +or -1. Yeah, that's. I think it's going to be 1, or if it's 1 or 2. And then for j equal to 2, it's going to be 2 times 6 +or -1. So it's either 5 or 7. And for j equals to 3, it's 3 times 9 +or -1. So it's either 3. It's either wait, what? It's either 12 or 15, right? So you see exactly 1 or 2 is -1, 5 or 7 is +1, 12 or 15 is -1, and etc. So yeah, so why pentagonal, first of all? Why pentagonal? And the answer is that I think the ones with the plus, j times 3j plus 1 over 2, these are called pentagonal numbers for the following reason. So I have another picture. This one is indeed from the internet. So if you try to, so what is happening here? 1, 5, 12 is I guess I have to take minus. 1, 5, 12 are these numbers when you take 3j minus 1. So this has to be a 3j minus 1. So yeah, the idea is that you kind of draw these pentagons which every time you increase a pentagon, it has, like this one has 2 points on each side, this one has 3 points on each side, this one has 4 points on each side, and etc. And then you count the total number of points, you get 1, and then 5, and then 12, 22, and etc. So, so that's the picture which you need to remember. And actually, I had to look it up because this is the pentagonal numbers, but what about the other ones? So j times 3j plus 1 over 2, the second number here, which is 2, 7, 15, 2, 7, 15, etc. These count. I think the easiest interpretation is they count the number of cards in a card house. Yeah, I don't even in a card house of height j, I think, or maybe, yeah, let me try to draw some examples. So here is a house of cards with 2 cards. Is that right? And here's a house of cards, 1, 2, 3, 4, 5, 6, 7. 2, 7, and the next one is going to be 8, 9, 10, 11, 12, 13, 14, 15, etc. So that's the interpretation of the other numbers. Yeah, I guess the correct English here would be house of cards. House of cards. And yeah, so that's the just if you're curious, but that has nothing to do with the actual proof. So how to prove this theorem? Let me copy the theorem again. Well, the idea is to try to come up with a bijection which kind of swaps the even and the odd parts. And yeah, if this was always 0, then I would almost immediately look for a bijection. But here it's complicated. There should be a bijection which does not quite always work. It should work whenever n is none of these pentagonal or house of cards numbers, but otherwise it should be a bijection. So that's more tricky than usually in this class. And yeah, so here is a proof. The idea is to use Young diagrams, but in a clever way. So let's me try to let's say I draw some Young diagram. So let lambda be a partition. Let lambda be a partition of n into distinct parts. Right, because both of these numbers only talk about distinct partitions, distinct parts. So okay, maybe something like this. Yeah, I don't know. Maybe, yeah, let me try this. So yeah, that's an example. Lambda is equal to 7, 5, 4, 2, something like this. Yeah, so the idea is to introduce 2 sets. One of them is going to be L sub lambda. Let L sub lambda be the bottom row of lambda. Yeah, let me try to remove the last part. So instead of 7, I'm going to write 6, 5, 4, 2. So L of lambda is the bottom row of lambda, which in this case consists of the following 2 boxes. That's L sub lambda. And also, let d sub lambda be it's sort of like the diagonal. I'm going to take the top right square, and then I'm going to just move down left as far as I can. So that's d sub lambda contains, well, d sub lambda contains the last box in each row I, such that which is on the same diagonal as the last box in the first row, such that lambda I is equal to lambda 1 minus I plus 1. So since the parts have to be distinct, it starts like 6, 5, 4, and then it drops by more than 1. So I only look at the first subsequence, which drops exactly by 1. In particular, for this partition here, I have 3 squares which form this diagonal. That is d sub lambda. Okay, and then the way the bijection is going to work is I'm going to try to either take these boxes and move them here, or I'm going to try to take these boxes and move them down here, depending on whether I have more blue boxes or red boxes in my Young diagram. So let me try to be completely, when you describe a bijection, you have to be completely precise. So define another phi of lambda, another, I guess, Young diagram. Young diagram, let me put it in quotes because we'll see what happens. But so there's 2 cases. Like one of them, if the number of red boxes on the diagonal is strictly bigger than the number of blue boxes, then move the blue boxes to the right. To the right of the lambda. I'm going to explain this in a bit. And otherwise, if the size of d lambda is less than or equal than the size of L sub lambda, then move the boxes of d lambda below into the new bottom row. So let me try an example. Let's say I take my partition from above. You see that this corresponds to the case d lambda, right? The number of red boxes is more than the number of blue boxes. So the size of d lambda is bigger than the size of L lambda. And therefore, my recipe is to move these boxes from the bottom up here. So let me try to draw what happens. 1, 2, 3, 4. Yeah, so there is going to be no. Okay. Yeah, I think it's going to be like this. So here are my red boxes from before, and here are the 2 blue boxes. Right, so I have moved the 2 blue boxes. I start from the first row and I append 1 box to each row, preserving the total number of boxes. And maybe I should try some other example. So maybe I have 3 boxes on the bottom. No, that doesn't work. Yeah, maybe something like this. So d sub lambda, the size of d sub lambda is only 1 box, so it's less than or equal to the size of L sub lambda. And therefore, what I do is I move this one box, right? Because by construction, because they're all on the diagonal, if I remove this, I still get distinct parts. So what am I going to get is something like this. What's going on? Okay, one box, and then, yeah. So the new red box is here, and the old blue boxes are where they previously were. Yeah. So, and now, once I have done that, now the bottom row is bigger than now the new L lambda is bigger than the new D lambda. And similarly here, now the new D lambda is at least as big as the new L lambda. So yeah. Anyways, what I'm trying to say is that applying this map phi twice recovers our original partition lambda. I wonder if does it make sense, or any questions up until this point? If d lambda is equal to L lambda, the two bottom rows have the same number of boxes. Okay, yeah, I think it should be the other way around, right? It should be, yeah, thank you. That is, so instead, this should be greater than or equal, and this should be strictly less. Strictly less. No, sorry, greater than or equal. This is strictly less. Right, I mean, that's, yeah, you want the result to be distinct. So if this d lambda is equal to the bottom row, then you move the bottom row. Yeah, let me try another example. If you had an extra thing in the bottom row, something like this, whoops, something like this, then you would move remove the bottom row, and you would move it to the right, and then you would still get distinct parts. Yeah. So for the equality, I want to move the bottom row to the right. Okay, yeah, but so yeah, the point is that it's what's called an involution. If you apply the operation twice, you get back to your original object. And so the claim is that it's almost a bijection. And another, yeah, I'm going to explain almost in a minute, but one other property is that you either remove the bottom row or you add a new bottom row. So you always change this. So phi changes the parity of the number of parts of lambda. So let me, okay, greater than or equal, and strictly less. So the only problem is that this is not quite a bijection, because it does not always produce the correct. It does not always produce a partition. So phi of lambda is a valid partition into distinct parts unless lambda is one of the following two, to j minus 1, to j minus 2, etc. J, or lambda is to j minus 1, etc. up to j plus 1. So let me try to draw an example, maybe for j equals to 3. So 5, 5, 4, 3. Here to j 6, 5, 4. So what happens to these partitions is that you look at the bottom row, and so L sub lambda and D sub lambda actually overlap. And so if you, well, in this case, in the first case, D sub lambda is at least as big as L sub lambda. So what I'm going to do is I'm going to move these boxes. No, sorry, I'm going to move the bottom row to the right. And what I get is, I mean, I just can't apply. Well, I mean, I can, but it's going to be weird. Can't apply the bijection here. And in the bottom one, again, they overlap. And yeah, so here I'm gonna take d sub lambda and I'm gonna move it to the bottom. And what I'm gonna get is, after I move it to the bottom, is I'm gonna have three parts. Three parts, yeah, something like this. So I'm gonna have, doesn't have distinct parts. And so in the first case, the size of lambda is 3j minus 1 over 2. In the second case, the size of lambda is j times 3j plus 1 over 2. And yeah, so other than these two cases, everywhere else it's a bijection. And that's why depending on the parity of j, right, you either contribute a plus 1 or a minus 1 to the sum. So that's the, yeah, I'm sorry, I'm a little over time, but that's basically the end of the proof. So if you have any questions, let me know. If not, there's no lecture on Monday, so I'm going to see you on next Wednesday. And that's it. Thanks. Yeah, have a good weekend.